So, whoa, wait. Right, okay, now it's recording. So the cryptography, oh, first I should mention, the Women in Cybersecurity chapter is looking for people to join. So check this if you're interested in being an officer in particular. The current highly energetic group that is doing a lot of good things there, I guess they're graduating and leaving, so new people need to move in. So be aware of that. College student clubs don't last too long here because of the 2-year rotation. But anyway, click that if you're interested. It certainly is a very good club, and men can join too. Anyway, I think I'm officially a member. Anyway, but they did a lot of good stuff. They get people tickets to go to like good trainings like SANS and conferences and stuff. So do a lot of good, yeah, they had a couple events here, so do a lot of good things. It's a good club. All right, so we're down to chapter 8, which is authenticated encryption. So let's start with that. All right, so all right, now a message authentication code that we talked about last week is a tag you put on a message to verify its integrity and perhaps also its authenticity if you use one as a shared secret, but it does not provide confidentiality. It's not encryption. It's just authenticity. It's like you download a file and they give you an MD5 hash you can use to verify the file. It's like that. It verifies integrity, but it does not protect the image. So for that, to get confidentiality, you need authenticated encryption. This is now encryption gives you confidentiality, but it doesn't provide authenticity normally. So that here you're going to have both features. Authenticated encryption is going to encrypt the message, and then it's going to also attach a tag, which you can use to verify that the message has not been altered and that you know where it came from. So that provides authenticity and integrity and confidentiality. That's what we want, and that's what a lot of people want. So we're going to talk about how this is done and talk about various techniques for it. So the simplest one is to use a MAC, a message authentication code like we did before, and there's 3 ways to do it. You take your plain text and you can encrypt it, and then you can also calculate a MAC and make a tag and just do these 2 things. This is encrypt and MAC separately. That's one way to do it. The other way is to calculate the MAC first, then encrypt the message and the tag MAC together. And the other way is to encrypt and then MAC. You encrypt it and then make a MAC on the ciphertext. These are 3 possible ways to do it, and in simple terms, they'll all work about the same. In practice, there are some defects where one system is better than another. So encrypt and MAC is in principle the least secure system because, remember, a MAC is not necessarily hiding all the information about the plain text. The only thing about a MAC is it's unforgeable. We talked about this last time. If you use a strong MAC like SHA-1 or SHA-2, then it's also random, but in principle that's not required for message authentication code. It could use one of those simpler hash functions that doesn't really conceal all the patterns in the plain text. It just is unforgeable, and therefore it might leak information about the plain text. This encryption channel is designed to really keep it private. This is not really designed for it, so logically, this is not the wisest procedure. Yeah.
Forgive me, sir.
Yeah.
Unforgeability is
Yeah.
mainly based on randomness.
Well, unforgeability would mean mainly based on length. There have to be so many that you can't find one. The length is probably the main thing, but the algorithm matters too. It just means there's no way for you to create an authentic tag without knowing the key. That's the idea. But that's not really the same thing as encryption, which means there is no way to recover the plain text without knowing the key. And that's why I say you have to be careful in cryptography to use the right cryptographic operation, because people would take encryption and take that as authentication. If you can encrypt something, that proves you have the key, but that's not really what it does. The purpose of encryption is to make it so you can't read the message without knowing the key. It is not to prove that you own the key. That's what authentication is. And people don't think this through carefully. And that's the problem here. You're using a process here that is not really designed to be encryption. So this might leak out information about the plain text.
Can I make a very fast detour?
Yeah.
In the context of network.
Yeah.
Wi-Fi network.
Mm-hmm.
I'm a computer. My computer catches the SSID of the network, and I'm asked for the password, so I'm authenticating.
Yeah.
And then after the authentication should happen the association. My computer is the cryptographic moment. When the cryptographic moment happens in the association, not in the authentication. Am I right? Or at least in between.
Well, there's like a 4-way handshake. You connect to it, you show that you have the password, and then you get a key just for you. which is different than the key that goes to other people. So the first few messages are unencrypted, and then they're encrypted in a way everybody can see them. And broadcast messages are encrypted in a way that everybody on the channel can see it, but your traffic, you get an individual key later. But you can deduce that key from the original handshake.
From the original, still the four handshake.
Yeah. That's why it does have a kind of weakness in that regard. Yeah. Anyway, it's pretty complicated too. But when you design a system like that, you really have to understand the cryptographic functions and what they are doing and what they're not doing. So SSH uses this technique. It's a pretty old protocol, so each encrypted packet, C, is followed by a tag, which is calculated with a key, a nonce, and a plaintext. Now, in practice, they used strong MAC algorithms. I don't know what they used, but something like MD5 or SHA-1. Like I say, people used strong hashing algorithms because they're just the ones that were lying around, and therefore it's okay. It doesn't have any problem with security. It's just in principle it could. But it doesn't. They use SHA-256, for example. So this, in fact, tag does not leak anything about the plaintext. But MAC then encrypt is another way. You calculate the MAC on the plaintext, and then you encrypt the whole thing. Now at least you know everything has passed through your encryption routine, so there's no way to reverse it without knowledge of the key. So that's good. This is more secure than encrypted MAC, and it hides the plaintext tag. So even if the tag is somehow related to this, you can't get it without the key. So that's better. The disadvantage is you have to decrypt it before checking the MAC, and that makes you vulnerable to denial of service attacks. I can send you invalid stuff, and you'll have to waste a lot of CPU decrypting it to find out it's invalid. And impossible that I could make it so after you decrypt it, it now has like code injection or something as it gets processed. So it might expose you to corrupted data. So that's a disadvantage of this one. And so, all right. This was used by TLS until version 1.3. And then encrypt then MAC is the best way. So you encrypt it, and then you calculate the MAC on the encrypted data. Therefore, everything down here, the ciphertext and the tag, it has been through the encryption, and the MAC is there, and now you can verify it right away on the ciphertext. So if the message is invalid, you don't have to do any more processing. And, that's the strongest system used by IPsec, the more modern protocol. And this is the pattern of everything in this course. The old protocols used something pretty weak, and they developed better algorithms as they discovered the flaws, and the more modern ones use better things, of course. All right, so an authenticated cipher is different from having a cipher and a MAC. This is the general solution to the problem. You're going to feed in a key and plaintext, and you're going to get a ciphertext and a tag. That's called an authenticated cipher. And to decrypt it, you need the key, the ciphertext, and the tag. And then you decrypt it. Now, in principle, you could decrypt it without the tag, but what you do is you verify that it's authentic and unaltered with the tag before decrypting it in practice. All right, so the requirements are the authentication should be as strong as a MAC, so it should be impossible to forge a ciphertext tag pair without knowing the key, private key, of course. Confidentiality is stronger than a basic cipher because in addition to being as strong as the other ones that you need to know the key, you also have to have a valid tag. So this will prevent chosen ciphertext attacks. Remember, this is one of the things that you can do, feed it arbitrary text and have it encrypted. Well, you can't do that because you can't make the tag. So that's stronger. So now the one that's actually used most of the time is this one, AEAD. Authenticated encryption with associated data. So you have data that is also carried in and it's not encrypted, but it is tagged. And this is the general solution. So now you feed in the key, the plaintext, and the associated data, and the output is the ciphertext, the associated data, not encrypted, and the tag. And you can use the tag to verify that both of these are authentic and having integrity. So now you can use this for either purpose. You can use it to accomplish what we had. If you just want a MAC, you can use it and just have associated data and a tag. If you want encryption, you can just have ciphertext, or you can have them both. And so that's the point. It'll be rejected if either of those don't pass the test of the tag. So that's the game. You can leave A or P empty, and then if you leave A empty, no associated data, then authenticated encryption with associated data is just authenticated encryption. If P is empty, it's just a MAC. So this is the general function, and the others are specialties of it, are special examples of it. All right, so now you want to avoid predictability with nonces, because this does have a problem. If I have another block of plain text that is the same, I'll get the same output. So it's got the problem we saw before where you can see the penguin. If you have blocks of data that are identical, the blocks of output are going to be identical. So it would be better to have something changing, and for that you add a nonce. Add a nonce here, a number used only once, so that even if you have another block of identical plain text data, it will not have the same ciphertext or tag. And this we're getting used to. Nonce stands for number used only once. This is a number which can only be used once and must not be reused with the same key. All right, so how do you make a good one of these? Well, here's the security criteria. You want it to be as strong as a good cipher, and you want the authenticity to be as strong as a good MAC. Then you're fine. Now, and there is a fragility. If the nonce is repeated, like we say, if you use the same nonce twice, then not only do you have the problem that if the plain text is identical, the ciphertext is identical, often there are other ways to find the key, and that's what happened to WEP. When you use the same nonce twice in WEP, a whole bunch of the bit stream is identical, and you can deduce information about the key.
WEP we said was not applying really crypto-like operations. Was
right.
Switching.
It took the first 24 bits of the key and called it a nonce, but it was only 24 bits. So after you do 2 to the 12 packets, there's a collision. Two of them use the same nonce. And that's the problem. And 2 to the 12 is not much at all. 2 to the 10 is 1,000. That's only 4,000. And that doesn't take long on a network.
2 to the 10 is 1,024.
2 to the 10 is right. So if you have as few as 4,000 packets, there are probably 2 with the same nonce. Yeah. And that means they have the same encryption key stream, and you can deduce something about the key from that, especially since you can predict most of the bits in the plain text in a wireless network, because the smallest packets are ARP packets, and they're the most common packets, and a whole bunch of them is always the same. So you actually know the plain text for a lot of it. So it's really turned out that you can crack into it really fast by collecting a lot of ARP packets. And
do we have any exercise that uses WEP?
Oh, I had a bunch of them. We used to do it all the time. I took it down because nobody uses WEP anymore. My students used to do it.
Just to understand,
my old course was like 10 years ago. My 123 course, we did it all the time. But it's hard to do anymore. You have to find a WEP router, and they're not easy to find anymore. Everybody quit using it because of this. Everything is WPA now, unless you buy really old stuff. Yeah. Anyway, all right. So here's some other consider performance criteria, like we talked about before. You might want to use counter mode instead of CBC mode, because in counter mode you can run it parallel on multiple processors. And in a mode like CBC, you can't. You have to do the first block before you do the second block, and so on. So that's another issue just for performance. And then you have internal structure. If you have 2 layers, like AES GCM, where you encrypt the plain text and then you have authentication, then you have to go through 2 steps. And it might be better to have something that all be done in 1 step. It might be faster. Yeah, it's a possibility. And then there's streamable. If you have a stream cipher kind of thing, then you can just continuously process a message block by block, discarding completed blocks. Non-streamable ciphers have to store the entire message, typically because they have to make 2 passes over the data. And if you think about the simplest one, where you would encrypt it, and then you'd calculate like the SHA hash, you might program it. So first you encrypt it, where you have to pass through it all, and then you calculate the hash by passing through it all again. And therefore you'd have to store the whole thing in RAM to do it efficiently. So it would be better to make it so you can do 1 pass on the first block and then quit having it in memory and go to the next block and not have to make a second pass. Just a performance matter. All right, then there's functional things. Some only allow the authentication tag to precede the plain text. Others can place it after or anywhere. And some require 2 algorithms, one for encryption and a different one for decryption, like CBC does. AES counter mode can use the same algorithm for both, so it might be cheaper and simpler to implement on low-cost hardware, that sort of thing. These are not exactly security issues. These are performance and practicality issues. So the standard is AES GCM. This is Galois counter mode, like we talked about. It's a version of counter mode, and it has some way to calculate these nonces that are used. So it's the most widely used authenticated cipher. That's why I added it to that project where you're encrypting the picture of a penguin, because this is the one we should all be using, is AES GCM. And it's approved by the NSA, part of Suite B, approved by NIST. So it's used by by a lot of modern protocols, IPsec, SSH, TLS 1.2. And so here's how it goes. It's encrypt, then MAC. So you take your nonce and you feed this into AES with the key, feed in your plain text, and it looks like you encrypt the nonce with a key, then XOR it here, then you feed in the associated data here. Anyway, pretty complicated. And by the way, it uses polynomial multiplication, which is a different kind of multiplication, which is more complicated for humans to understand, but it's better for computers because you never carry anything. So it's a different form of multiplication. Anyway, that's what it uses. It's a little hard to understand, but it's designed to get the job done. And the problem, of course, is if the nonce is repeated, then it's fragile. Then the AES part of it is identical, and if you use nonce twice, they can get the authentication key and forge tags. So that's a fundamental problem. And in 2016, they found HTTPS servers that were using repeated nonces, including a bunch that were just using a nonce that was all 0. This is the kind of mistake that made me want to teach this class. When I looked in Android apps and they were all making stupid mistakes like this, you're supposed to have a nonce and people don't know what it is, so they just set it to 0. This just came out last week. There was a major processor, I think it might be AMD, but it turned out that their firmware in the processor was signed, but it was signed with the example key from the NIST document, not a real key. All the same key and all just the well-published example key. This has happened many times. People implement encryption by just copying the code from like the NIST standard and just using it, and they don't even know you have to change the key or change the nonce. This tends to happen. Obviously, people are implementing cryptography, they just don't even know what they're doing at all. And that's why I think even a basic course like this would have helped them, where you just practice using the pieces and understanding what the pieces do. Anyway, so GCM is parallelizable. The MAC is not. It's streamable, or that's something. So it's not perfectly efficient. All right, so there is a better one. Like in every one of these chapters, there's always a new one that's better that nobody's using yet, and that's OCB, Offset Codebook. Been around for a while, since 2001, faster and simpler than GCM, but it was limited by a license, but now apparently that's out of license. So it blends encryption and authentication into one layer with only one key, and each block is encrypted with a block cipher, with a key and an offset computed from the key, and a nonce that increments for each block. And so the tag uses XOR operations, XOR S with an offset computed from the last, and it just keeps XORing in a block so it doesn't have to look at it again. And it also supports associated data. So, as you expect, it's considered quite good. If you repeat the nonce, it's not so bad. You'll be able to see identical blocks of ciphertext, but you won't be able to deduce the key from it, so it's more resistant to that flaw. And they're both very equally fast, parallelizable, and streamable. On early processors, it used to be 3 times faster, but now apparently they're both about equally fast now. So, like so many things, in principle it's better. In practice, the improvement is not large enough to make anybody move. The old system is almost as good, and nobody's going to bother moving off it unless some terrible flaw is found in it. This is usually the case. And I have to agree, you want to use the official standard. Don't use anything new. I would say the same thing. Use the official standard as long as it's the standard. Until there's a good reason to move, I wouldn't move. You don't want to be the guy to find out there's something wrong with the new one. Anyway, so SIV is another one. Synthetic IV in authenticated mode. This is what I can use with AES. Even if you use the same nonce twice, it's fine. You got an encryption function, a pseudo-random function, 2 keys, and a nonce, and you add them all together. It's not streamable. It has to keep the whole plain text in memory, so that's annoying. If you're encrypting large things like many gigabytes, that's an issue. But it is considered the most secure. But like I say, the older one is, as far as anybody knows, perfectly fine. Just in principle, it's not as strong as these later ones. And then there's permutation-based ones. If you don't want to use a block cipher, you can use another system, permutation-based, where you start with an initial state, and then you XOR with a key and with a nonce. Well, the key and the nonce are appended to make this, and then you permute with plain text blocks. So this is like RC4. Remember, RC4 just shuffled the bits around like cards. It's going to permute them. And that produces a series of pseudo-random blocks. You then XOR them with plain text blocks. So you have this mixing the bytes and then XORing it is all you're doing. So the operations are very simple. And so that's the game. And you have this internal state you keep changing, and then you take some of those bits to form the tag. So the security relies on secrecy of the internal state. You have to pad the blocks carefully. Nonce reuse is not a big problem. And it's streamable, but it is not parallelizable. You have to do the blocks one by one. So, overall, it's got some advantages, but like I say, not enough that anybody would really move off the standard to this thing yet, I think. So, what can go wrong? Authenticated ciphers must provide confidentiality and authenticity, and by the way, integrity. So you have two values, plaintext P and associated data A. You want it to remain secure for all values of P and A, even if you're going to have one of them absent, if you're going to make them identical, if you're going to make one of them all zeros or something, you have to make sure that none of those leak out information about the key. It must remain secure against attackers who collect numerous message tag pairs. Even if you have a lot of them and you analyze them, you shouldn't be able to find anything. That is referring, of course, directly to WEP. That was the WEP attack. You pump your network with ARPs, you collect about 50,000 ARPs, then you find the ARPs that had identical IVs, and from that you deduce a lot of information about the key, and that lowers the key space down to a small space you can brute force it. That's how the WEP attack worked. So you have to consider that somebody might do that. They might collect thousands or millions of messages, message tag pairs, and there should be no way to use that to deduce the key. And in WEP, there was. So AES GCM uses the hash key over and over for each block, and certain values of hash make the tag weak, and this, by the way, is also true of RSA. You have a parameter, and you're taking it to higher order powers, and there are some values that you repeat in a little loop when you do this. We talked about it in the row model for hashes. So that's why this is one possible weakness. If you had a bad hash key, then these would not keep being random. They would just go around a little loop of repeating the same numbers over and over. And if H, for example, had a cycle of 5, then you could swap blocks of ciphertext. So suppose H to the 5th is equal to H. Well, then the first and the 5th block are in fact encrypted with the same internal value, so you could swap them. You could replace the 1st and the 6th, and it would still match the tag in this system. So this is a form of tag forgery, and I've done this before, and this was also an issue when we did DES ECB in the web application class. You have blocks of data. They're each encrypted independently in electronic codebook mode. There's no cipher block chaining or anything, so you can take a block of data and flip it with this one. You could, and it would still be valid. And if you do that, then here you have UID equals 0. See, UID should have been some other number, like 1, but when you flip these two blocks, UID changes to 0. So that's a form of tag forgery, where you can modify the encrypted message without knowing the key and still create something that will pass the test. So that's a flaw. And that's a flaw this system has if you're unlucky and choose a bad value for H. And there's a periodicity here. That's pretty exotic. It would be hard to detect that, but in principle, it's a weakness of the system. It's not practical to exploit. You have to find that cycle length, into theoretical exploit, but not very practical. And also, you can, in principle, produce short tags. Normally, it's 128 tags, which are fine. But of course, if you made a short tag, like 32 or 48 bits, then that would be too weak, obviously. It'd be pretty easy to find a collision of a tag like that. So if you do choose to shrink the tag length, then you're greatly lowering the security of the system, which is pretty obvious. Anyway, let's try the Kahoot. And this was chapter 8. Yeah. So I go here and here, and there it is. Good. All right.
search on Amazon.
Yeah,
And I copy and pasted the resulting URL of a specific product that I
Yeah.
potentially buy. I noticed that the URL is 1 kilometer long.
it is. And it's all full of parameters, and you can delete a bunch of them and it doesn't matter. And you could swap a bunch of them, and some of them could be wrong and it wouldn't matter. Those parameters are often not very important. They're like an advertising ID and stuff like that. In fact, this is something we do in the web hacking class. If you want to find out, I've done this in Amazon. In fact, I researched Amazon security. I took a request, put it in burp, and then started deleting all the cookies. And you can delete all of them except one, and it still knows who you are.
Okay.
Most of them are really not very important. They're used for internal tracking of traffic or ads or something.
My suspicion was that it was including my information because, for example, Amazon geolocate you
Yeah,
in order to redirect you
well-
to products that are more pricey or less pricey according
Yeah.
to the median income of the area where you are searching.
Yeah, well, I think they're tagging all sorts of things, like what advertising campaign you're seeing, and maybe what discount you're getting, and all sorts of things. But only one of them is needed to identify you, and you can find out in burp. But yeah, and in general, they're probably all bad for your security, bad for your privacy. I mean, But anyway, yeah, I've done that all the time. In fact, when I post news links with links, I trim all that stuff off. Yeah, but that is an issue. All that is keeping track of something about what you've been doing that's probably none of their business. Yeah, absolutely. Anyway.
I was surprised. I mean, the URL was.
I know. I know.
10, 15 line long. Almost.
I know, and I don't know why they put it up there where you can see it. They could put it in the post data where you wouldn't see it, and it wouldn't irritate the customer so much. But anyway, it's you're absolutely right. That's a strange thing they do. Oh, and see, I guess this is okay. I think I need to make it. Oh, well, I guess we're okay. All right. So let me start it. All right. All right, so which one of these does not give you confidentiality? Very good. The message authentication code just provides authentication, not confidentiality. All right. All right, which one is the NIST standard? And, you know, from 90% of companies, and probably anybody I would deal with, this is the end of the discussion. If there's a standard, just use the standard. Don't argue. It's there for a reason, you know. You'd have to have a really good reason not to use the standard. But if you can, you always want to use the standard because all the companies you do business with and all the other people you work with expect to see the standard. And if they don't, they're going to be suspicious, like, what's wrong with you, for good reason. You'd have to have a good reason not to use the standard, anyway. And it's AES GCM. All right. All right, which one might leak information about the plain text? Yeah, encrypt and MAC, because the MAC might not conceal all information about the plain text, and you're letting the plain text go straight to the MAC without passing through encryption first. All right. All right, which one can tag data for authenticity but not provide confidentiality? It doesn't always do that, but it has the ability to do it. Yeah, that's AEAD. The associated data part is what's described here. You can send in associated data, and it will not be encrypted, but just tagged for authenticity. It can be used that way. All right. There we go. Good. So I'm going to stop this recording.